So in this short video, I want to continue talking about the X and P representations. P representations. And talk a little bit about how to expand functions in these two basis sets and so on and so forth. So let us briefly recall that, for example, in finite dimensions, one of the first things that we discussed was that there is nothing sacred about a choice of basis, right? It depends on your problem. It depends on the problem at hand. For example, I can write any vector alpha as a linear superposition of, let us say, some AI, EI, where my choice of basis sets is EI, right? And I can always go to a new basis set. EI goes to EI prime, right? Such that they are related by some unitary transformation. EI, let us say, is equal to some UIJ EJ prime, okay, where the summation over J is implied. Now I can expand the exact same vector alpha as AI UIJ EJ prime, right? And AI UIJ I can call, so there is two sums here. So this AI UIJ I can call by some different symbol where this summation over I has been implicitly done. So this is a summation over both I and J. And this I can call some Bj. So I can write this, the exact same vector alpha as sum over J, Bj, Ej prime, right? So as long as I know how the two basis sets are related, I can always expand the exact same vector in terms of any one of the basis sets. The choice of basis sets depends on the problem at hand. So you choose the basis set that makes your life easy. The exact same considerations apply to infinite dimensional Hilbert spaces as well, particularly for the X and P representations. So let's quickly recap. In the X basis, the X basis, well, the X basis is defined by the eigenvalue equation for X. X acting on the X is XX. And you know that the eigenfunctions are basically delta functions. So X prime X equals delta X minus X prime are the eigenfunctions of X in this basis. Okay, and in this basis, the eigenfunctions of the P operator, excuse me. So let's actually define the eigenvalue problem for the P operator. P acting on P is PP, right? Where this P outside the kit is the eigenvalue, which is a continuous variable. Now, if I take the inner product of both of these, both sides of this equation with X, we already discussed that the representation of P in the X basis is basically minus IH bar ddx, right? So if you plug that in, you'd actually get minus IH bar ddx of XP equals P XP, right? And this XP, this quantity XP, we can write as psi P of X, right? And this turns into an eigenvalue equation, which is IH bar ddx psi P of X equals P psi P of X, which has the solution psi P of X, which I remind you again is the overlap XP, is some A e to the minus I Px over H bar. I'll try to get the factors of H bar and the overall factors right in this lecture. Let us see how successful I am. Now I can always choose my A, psi P of X. I'll choose my A as 1 over 2 pi H bar e to the ipx over h bar. And this choice of the normalization constant, my orthogonality works in this particular fashion. Psi p prime star of x, psi p of x dx, if I integrate minus infinity to infinity, this is basically delta of p minus p prime. Okay. So again, the eigenfunctions of both the x operator, which is a delta function, and the eigenfunctions of the p operator, which is e to the ipx over h bar, are both in some sense a little weird because the eigenfunctions themselves cannot represent physical systems because they are not normalizable functions, but they are orthogonal in the sense of the delta function orthogonality, and I can always use them as basis sets. Okay. So just like I can expand any vector in a finite dimension as a linear combination of the basis vectors, I can represent any vector. Let's call this vector f, right? In the x basis or p basis. How would I do that? Well, I will simply insert a complete set of states. Remember our completeness relation for finite dimensions is ei equals identity operator. And in infinite dimensions, for example, in the case of x, this is equal to minus infinity infinity dx, x equals 1. Right? So suppose if I want to expand a vector f in an infinite dimensional Hilbert space as a linear combination of the basis vectors of the x operator in the x representation, I would simply write this as 1 acting on f, right? And that is just trivially equal to f. And instead of the 1, I will simply substitute the completeness relation minus infinity infinity dx, x, f. Okay. And this overlap of x, f are simply the components of this vector f in the basis x. So just like the vector alpha has components ai in the ei basis, just like this, right? So this vector has components xf. And this xf we call the component of f that lies along the direction x. Of course, this is an infinite dimensional space, so the components are basically continuous functions of x. So I can write this vector f as minus infinity to infinity dx f of x, x. Okay. So just like I can write a finite dimensional vector as a linear combination of the basis vectors, I can also write an infinite dimensional vector as a linear combination of the basis functions in this particular fashion. Okay. Now I can expand the exact same vector also in the p basis. For example, in the p basis, in the basis set provided by the eigenfunctions of the p operator, how would this vector look like? F. Again, I will write this as 1 times f, but now I will insert the completeness relation as pertaining to the p operator. So if I do this, I get minus infinity to infinity dp pf. Okay. And this, just like the overlap of x and f are the components of the vector f along x direction, the overlap pf are the components of this vector f along the p direction. Okay. So I can write this guy as minus infinity to infinity dp f of p, p. Now notice that I have not done anything to the vector, right? The vector remains the same, but if I express it in different coordinates, of course, the expansion coefficients change. So our job is to try and understand what the relation between these expansion coefficients are. So again, to go back to the finite dimensional example, I know that if I can relate the two basis sets by this particular linear transformation, ei equals ui j e j prime, I can always re-express my vector in terms of the new basis set. So what is the linear transformation that takes me from the coefficients in the x basis to the coefficients on the p basis? Well, let us try to figure this out. What is the relation between f of x So what is the relation between f of x, the components of the vector, the x basis, and f of p, the components of the same vector in the p basis? Let's work this out. So I'll start with f of, let us say, p, which is equal to pf. That is our definition, right? Now in this, I will insert a complete set of states between p and f. So I'll write this as p1 acting on f, and I will write this as p integral minus infinity to infinity dx x. Okay, so I'm simply inserting 1, and I'm inserting a complete set of position eigenkets. So I can pull out the integral sign, I can pull out the integral dx, and I will write this matrix element as p hitting x from the left and x hitting f from the left. Okay. Now remember, now let's be a little careful with the signs. So this, so if you go there, so the overlap of x and p is given by a e to the minus ipx over h bar, which means the overlap of px is the complex conjugate of this guy, because the inner product of alpha beta is the complex conjugate of the inner product of beta alpha, right? Okay. So I can write px as 1 over square root of 2 pi h bar e to the plus ipx over h bar. So f of p equals minus infinity to infinity, excuse me, I'll pull out the 1 over 2 pi h bar out, minus infinity to plus infinity dx. Now notice that the overlap of x, f are basically the components of the vector f in the x basis. So this is basically f of x. So I can write this guy as e to the I px over h bar f of x. So the components of the vector in the p basis f of p equals integral dx e to the ipx over h bar times the components of the same vector in the x basis. And this is an important relation, and I'm sure you've all seen this relation before. It's called a Fourier transform. Okay. Similarly, if you start with, instead of starting with f of p, if you start with f of x equals x f, and you insert a complete set of states like this, right? And I can write this guy as minus infinity to infinity dp xp pf, and if I recognize that this quantity is basically f of p, I can write this whole thing as 1 over square root of 2 pi h bar integral minus infinity to infinity dp e to the minus ipx over h bar f of p. Okay, so these two relations basically tell you that if I know the components of the vector in the x basis, I can easily know what the components of the same vector are in the p basis. And f of p is said to be the Fourier transform of f of x, and f of x is said to be the inverse Fourier transform of f of p. So these two guys are the Fourier transforms of each other. Okay, I'm sure you have seen a little bit of transforms, and Fourier transforms are very important in quantum mechanics because they tell you how to relate a function in the x basis with the same function in the p basis. Okay. Now there is a slightly more tricky question that we can ask, and I will tell you how to approach this, but we will solve it in the tutorial. Notice that we said that the uh, representation of the P operator in the X basis. Oops, wrong color. P operator in the X basis is basically minus IH bar ddx. Now I can equally well ask, what is the X operator excuse me, in the P basis? Okay, I'm going to leave this as a homework for you, and I'm going to include this in the tutorial also because it's a very important calculation. But the way you go about doing this is pretty straightforward. So there is two different ways in which you can approach this. They are both almost equally the same. A slightly more straightforward approach is to start with the commutation relation x comma p equals IH bar times the unit operator. Notice that this is an operator relation, excuse me, and so this is valid in any basis, okay? Now, when I say that I want the X operator in the P basis, what I basically want is, suppose if I take any arbitrary vector psi, how does this quantity look like? Okay, I want to understand what this quantity is. So to understand what this quantity is, you start with this fundamental commutation relation and sandwich this between a P on the left and a psi on the left. If I sandwich P on the left with psi on the right, well, the right hand side is pretty straightforward. It's the overlap of P with psi. It's basically the components of the vector psi along the P direction. So this is IH bar psi of P. Now you simplify the left hand side using the completeness relation, and then you would be able to guess what the X operator in the P basis is. So I want you to finish this computation using this particular method. But if there is any other method, you can also use this. For example, you can start directly by asking what is this matrix element, okay? And then you can go ahead and insert a complete set of states here. So minus infinity to infinity, Px, x, x. Now I'll insert a second complete set of states, x prime, p prime, and I will integrate over both the guys. The reason I will do this is because I already know what the X operator in the X basis is, right? That is just a delta function. So this guy is basically X prime delta X minus X prime. And I know that these are basically the psi p star of X, and this is psi p prime of X prime. And I can utilize these things that I already know, and I can figure this out. So you can either follow the first method or the second method. And using this, please try to figure out what are the components of the X operator in the P basis. You'll actually find that the components of the X operator in the P basis is IH bar ddp, okay? Just like the components of the P operator in the X basis is minus IH bar ddx, the components of, the representation of the X operator in the P basis is IH bar ddp, okay? This is what you should ultimately find. So the point of this short lecture was to try and tell you two important points: that the approach to infinite dimensional Hilbert spaces is reminiscent of the approach to the finite dimensional case, in that you always express the vector as a linear combination of the basis vectors, just like you express any vector in a finite dimensional Hilbert space as a linear combination of the basis vectors. But the relationship between the components in X basis and P basis is also a unitary transformation, and this is called a Fourier transform. And this is something that will be very useful as we progress in this course. So please make sure you grasp this completely. Okay. All right. So I will stop this short recording at this point, and then we will continue in the next lecture with solving the Schrodinger equation.